Hello everyone. So let's get started. So since there was a lot of trouble yesterday during the tutorials and so on to try to install many of these packages, especially for Windows users, there are a couple of solutions. One is to install this Windows subsystem for Linux or something like this, WSL as it's called. If you use that, then hopefully many of these problems will disappear. The other is even people who have Linux, if they are having trouble in installing things. I have put together something which works on Psi server. So this is a science server which has been created by Johns Hopkins University. And so if you log into that, you can create an account on that environment, and it will allow you to get a Jupyter Lab or a Jupyter Notebook and things like this. So how to do that, etc. I've put a gist together here. So if you click this link, you will see detailed instructions on how to install both GW Cosmo as well as Icaro GW, how to run the bright Siren posterior that we have done so far. And so please take a look at it in case you have trouble. And for people who have trouble following those instructions, then I've also put together a screen recording that I did for whatever steps I followed. So those are also pasted here. So just how to start a compute server on Psi server, that's shown in the first video. And then once you have the instance, the compute instance, then how to install. It's just some copy pasting of commands, but then it should be all set up. Okay, so please follow either these video links or the gist, and then it should work. And then if you have trouble, let us know. But at least here, if it works for one, it should work for everyone in principle, because it's a very uniform environment. Okay. Okay, so towards the end of the last lecture, we started to talk about a Bayesian analysis in order to understand how to get parameters, especially the parameters that we are talking about are the rate parameters. So what is the distribution of masses, what is the distributions in redshift, and so on and so forth, that you can try to get by carrying out a Bayesian analysis over the gravitational wave event data that you get. Right? And so we started with big parameter set, cosmological parameters, parameters that define the shape of this distribution, what is the probability distribution of these masses and spins, etc. And then one normalization parameter, which will tell you how many gravitational wave events form, okay, within a given volume, for example. Then we said that, okay, for the moment, let's ignore cosmology. So this omega goes out. What you're dealing with is only these shape parameters on this end. So this lambda given the data, this is just pure Bayes theorem. It is data given lambda times the prior on this lambda, the prior on the parameters divided by this evidence. And the parameters that are drawn from this population shape, we'll call them theta. Okay, so theta will include the mass, spins, etc. And so the number of events for a particular given theta, you can express it as the total number of events times this shape. So the population shape. So in the end, what we are after is this population shape parameters. Okay, and also this n, but as a function of redshift in principle. Okay, so this is just a recap. So I wanted to again, what's going on? Yeah. Okay. So how did we write these things? So basically, we need to have this, right? P pop theta given lambda given this. How do you get to this? Yeah. So P lambda given di is P di given lambda. So we need to figure out what this likelihood is, right? How do you get the data given the lambda? So for the moment, we assume that there are no measurement errors. As soon as you are given the gravitational wave data, you can figure out what are the exact parameters that describe this event. If that is the case, then in that case, you can work out what is the probability of these observing the theta I parameters given your shape parameters, given the parameters of your model. Right? And then this, what is this theta I? So this is theta I vector in some kind of set form, which means if there are n events, each of them have parameters, and those are theta I. Okay, and each of these theta I will consist of these masses and spins and so on. Okay, so you can then write it down for only one event, say p theta I given lambda. What is that? So that probability is just given by this thing which is inside this multiplication symbol. For the moment, forget about the multiplication symbol. So it is basically just what is the probability that you get a theta I given the parameters, given the shape parameters themselves, and then you normalize it. Right? So this is assuming no selection effects whatsoever. Yeah. So this is how, as I said, if you roll a dice, if you wanted to figure out the probability, this is how you will do it. There is the probability of getting a particular event divided by the sums of all the probabilities. Right? So this is normalization. But you have n observed independent events, and so you multiply each of those probabilities. So that's the reason why you get this kind of an expression. But then I said that you won't be able to observe all of these events. Some events will be censored just because maybe they don't have enough signal to noise ratio. Maybe it conflicts with some astrophysical signal, non-astrophysical signal, right? So you may want to get, or you will get rid of eventually some of the events that you have observed at the GW detectors, because they may not be real or you are not certain about it. And so then in that case, the probability to observe a given theta I given lambda prime, it gets modified by this detection function. Yeah. So not all events which have a given set of parameters, you will be able to observe. And that's the thing that we have put in here, both in the numerator and the denominator. And again, whenever you have trouble understanding some of these equations, you go back to the dice rolling question and you say that, okay, when I'm rolling the dice, I'm not able to observe a few of these events. Then how will I write the probability, right? And so you will end up with this expression in that case. And again, the multiplication over the n of events is still there. So then we said that the detection probability for events that you have observed has to be 1 because you have observed these events. You have said that they go into my event set. And so this thing in the numerator is exactly equal to unity, so we got rid of it. But then the rest of this thing remains as it is. So this is what you would do if you had completely noiseless vectors, no measurement errors whatsoever. So given observations, you can figure out exactly what the theta is, except for selection effects, right? So that's what we have written down. So now, then we said that let's go to a case where we have noisy data. So in that case, what do you do? So this detection probability that is there, this gets modified. So now we are saying, given a theta, you will have certain data vectors, right? So there are different possibilities. Given the noise realization, you will get different data sets, right? Even though the underlying parameters are exactly the same. And so here is some kind of a marginalization over D that you can see, right? And so you say P of D given theta, D over all possible data vectors that you generate. This is in principle over all possible noise realizations, right? And then only certain events you can detect, say where the SNR goes above the threshold, for example. And so this thing, we wrote it down more generally as again integral over all data vectors, but then putting in this I, which tells you whether a given data vector will be detected or not. So once you add this, you can write down the denominator, which is here, right? This p det of theta. You now plug in all these equations. You see what it will look like. So that goes in the denominator, right? So this denominator here is basically this alpha thing as written. And then in the numerator, we just had p pop theta I given lambda, but now you are going to have an integral over all possible data vectors. Over the data vector that you have observed, right? So this data vector is what you have observed, but there are all possible theta values that can give that data vector. Yeah, because the observable is now the data vector and not theta, right? The noisy data vector. So what is the noisy data vector given these parameters? It's an integral over all possible thetas that can give that noisy vector. And so this is what, for a given event, it simplifies to. Now, if you have many, many events, then there will be a multiplication. Yes. Right. So this SNR threshold is a choice that is made when analyzing GW events, right? Yeah, indeed. So they carry out studies where they ask, given the background, how many false events do you expect compared to true events if you use a particular SNR threshold, right? So they will do all sorts of studies in order to figure out what this threshold should be. But then you also try to make it such that you are not affected by the threshold, or you will try to check what happens if you vary the threshold, how much are your results sensitive to that particular threshold that you have chosen. Okay. So if you look at the LVK cosmology papers, for example, in the early days, we would do analysis, or even now, where we change the threshold and see how our cosmological constraints vary. And I think similar things are done even in the rates and pops paper, so rates and populations. So typically people have used something like SNR threshold of 12, which you may think is quite large, but that's what has been used for cosmology analysis previously. Okay. So, if you decide to use a threshold which is lower, then you better also have a model for saying that, well, how many false events can get into your sample, right? So when you are a Bayesian, if you say that, okay, either you will say that my prior says that if I choose a threshold which is really large, I don't have to worry about this population. Or the other way, if you say that I will take everything, but then you need to have some sort of a model for what this background is going to. Okay. Right, so the statistical errors will go up, but it's a question about precision versus accuracy, right? And so if you have, like, you can get really, really precise values, but they may not be accurate. So there will be bias and so on and so forth, right? So that you have to worry about. And that's the reason the way that these tests are done, you say that you will change the thresholds and see how much of an impact it has. Of course, the error bars go on. Okay, so is everyone with me until here, right? So right now, we went to a noisy data vector, which was these di's instead of having theta i's. So we started with a simple expression for theta I, but then we arrived at what happens when you have noisy data vectors. That's where we will be often. Okay. So in the gravitational wave case, so let's look at this expression now. So this is something to do with the detection probabilities, right? This does not depend upon each and every event, okay? Because you see that there is no D here, right? In the denominator, there's no data here, okay? So this thing I can easily take out, okay? This detection, selection probability, selection effects that are there, this thing I can take out outside of this multiplicative sign that we have, right? And so you will have this denominator raised to minus n ops. That's what you will get. Right? Okay, so this thing you can determine by doing many, many injections and trying to figure out what are the theta values that you can actually detect, okay? And you need to assume certain population parameters in order to do that. So you will assume a set of population parameters and carry out these kind of detection probability calculations okay? But then you may say, well, there is a dependence on lambda prime as well here. And so hold on to that particular thing. You try to sample from a large number of injections, which covers a large number of parameter space as well. And finally, whatever lambda you use, you try to reweight in order to get this selection function. So we'll get there at some point. First, let's focus on the numerator. Okay, this p pop theta given lambda, this is some probability distribution given your lambda prime parameters. This describes the shape of the distribution. So you can always write down what is the population, what is the parameter theta given a lambda, because that's exactly what this lambda prime is supposed to tell you, right? So this is not a problem. This is just telling what is the probability given your lambda primes. Right? This is not an issue. What we want to know is how to get this, p di given theta. So what is the likelihood of getting any gravitational wave event data given a set of parameters theta? Okay. So this is what is called parameter estimation, right? So this is what is done when you see the gravitational wave event data. You get some strain data, as I had shown you before. You take that strain data and you try to calculate what are the theta parameters that are relevant given this strain data. Okay, so then you have to write down this likelihood. Now, thankfully, in the gravitational wave case, what happens is as soon as the data comes, even before any of these rates and population study are done, there are parameter estimates which are already run. And these parameter estimate runs include these Monte Carlo Markov chains. And so they give out a posterior already for what are the parameters given the data set. So they give out this particular thing. Okay, what is theta I given the data from the ith gravitational event? These are released to the public nowadays already. Not the final P runs, but at least the preliminary ones, they are already released to the public. Okay, so that if there are certain astronomers who want to go and follow up, they need to know where exactly in the sky I need to go and search for a counterpart for this event, right? So that is one thing. So what are the kind of masses for these events? If these are binary black holes, maybe I don't need to follow up. But if this is a binary neutron star event, then maybe I want to follow up. So these parameters, this thing, the posterior of parameters given data, this is something which is already, that information is given out. Okay. And before doing the cosmology and the rates and populations analysis, this becomes available. The finalized posterior distributions of parameters given the data sets, this becomes available to the team. Okay. So if this is available, but we want this, the likelihood, so what do? You use Bayes' theorem, right? So you multiply this by the probability of data, divide by the priors. And so this will remove out the priors. Okay, so while calculating this posterior, the parameter estimation team would have assumed some priors. You would try to get rid of them. Okay, because you don't want their priors to affect your analysis in the end. And so you can use Bayes' theorem basically to write down this p di given theta as this. Now I said that this posterior distribution will be given. What does it mean? What it means is they don't give you actually the value or a function which tells you what is p theta given d. What they instead give you are samples. Okay. So again, let's go back to the dice case. Okay, if I wanted to ask you, okay, what is the average value that you will get if you throw the dice 1,000,000 times? What is the average value that you will get? Then one thing that I could do is I could assign a probability to each of the events, so to 1, to 2, to 3, 4, 5, and 6, and tell you what this probability is. Or instead, what I could do is I could roll the dice 1,000,000 times, and I could give you all these outcomes. Okay. Even if I do that, you should be able to figure out what is the average value that I should get when I throw the dice, right? So the same thing these people will also do. Instead of giving you this, they actually give you samples from the posterior. Okay. So they would have run some kind of Monte Carlo Markov chains, and instead of giving you the direct posterior, they would give you samples from the posterior. And if you have samples from the posterior, then you can work out all of these quantities. What is the mean? What are any other functions of the parameters that you should be able to work out? Okay. So that is what is done here. So you look at this P of di stays, this P di given theta that was there. Now it is expressed like this. Okay. So this, there are SI samples for the ith event. Okay. And that's the reason why this sum now goes over j equal to 1 to SI. And then you have the population parameters. So what is P pop theta I given lambda prime? So this you can compute because you have a model for what this lambda prime is. Right? So this you can compute. Okay, multiplied by this P di and divided by this prior pi of theta. Okay. So P di given theta, now you have expressed it as an average over the samples that have been given to you, the posterior samples that have been given to you. From there, you work out the likelihood by taking this prior out. Okay. So everyone with me until here? Or difficult to follow? Just tell me, okay? So thus far, that's where we have gotten, right? And so we are using basically this SI samples that are given for each of the events and then putting it in our expression for the entire likelihood for the data set. And so once you have that, then now you go back to your Bayes theorem because what you want is not di given lambda, but lambda given di. And so that will be the prior, the evidence here, and this likelihood that we had written before. Okay? So this is just taking this, putting it here. Okay? And again, you can see, you go back to our cheat sheet, this is just Bayes theorem. Okay? This evidence here, which was here, it will cancel out with these, the multiplication of these evidences here, because each data set is independent. And so this goes out, this cancels out with this. All you are left with is the prior and then this division, except other than this P of t. I'm sorry? How is the sampling done? So that's where these Monte Carlo Markov chain techniques come in. Because what they do is they give you samples from the posterior distribution. So I mean, it depends upon how you do it. So people do it either using nested sampling or you can run EMC and things like this. I think most of the time in GW case, it's done using nested sampling. And so each of these samples are not exact, I mean, they are independent, but they are not equal weight. So there is a weight associated with it. So you have to use that weight as well. Okay, so now you can see this explicit dependence upon the priors on the hyperparameters. So you may have some prior information about the hyperparameters so that you can see easily. You can also see how the likelihood is actually for each of these events is also going. So all of these things you can see how the selection effect goes in. So this is selection effect term, this is the likelihood term, this is the prior term. That's what makes the posterior. Yeah. Okay. So that was about the shape parameters. Now we have to deal with the numbers of events that you observe because there is also an amplitude. Right? And so for the amplitude, you are observing some n-obs events, right? Some observed number of events. So this n-obs number of events, they will be basically a Poisson draw from the expected number of events that you expect to detect. So there are certain number of events that you expect to detect, but you will only observe some integral number. It won't be exactly the same. In fact, the number of detectable events, this will be the total number of events that you have. So dn by d theta is a function of lambda. So given your hyperparameters, what is not only the shape, but also the distribution of these different parameters given your parameter set, right? And then what are the data sets that you will get given this theta? And then you have to integrate over all possible values of theta and over all possible data vectors, over all possible noise realizations. This will tell you what is the possible observable number of detections, right? Remember, this will not be necessarily an integer number, right? So this is some kind of a mean. So you expect some n number of events to be seen. And that n will not be an integer, maybe 3.5 per day or something, or maybe 1 per week, some 1.5 per week. These kind of numbers you will get, non-integral. But in reality, you will observe only an integral number of events. And so this thing will be distributed like a Poisson likelihood, n knobs given the number of detections that you expect. So that is just e to the minus n, possible e to the minus mean number of events that you expect, and then the mean number raised to this power n ops. Okay? And so then the final likelihood, the final posterior distribution for the shape parameters as well as the amplitude parameters, given the gravitational wave data, it will depend upon the prior on this lambda prime, prior on n, right? And then the likelihood that we had written, di given lambda prime, as well as what is n obs given the ndet, the detections that you expect, the mean number of detections that you expect. Okay. So this is the final expression for the hyperparameters of the CBC population. So this compact binary coalescence is what populations are generating these observed events. If you want to figure them out, then you have to work out this posterior. Okay. So these posteriors are the ones that are being basically coded up, right, in GW Cosmo or Icaro GW, in order to give you what is the distribution of parameters that finally gave rise to the events that you see. So, okay. So again, prior information is here, likelihood is here, and then so sorry, this is not prior information. Sorry, this is the prior information on lambda prime and pi of n, and this is the Poisson, the number of events that you detect given the total number of detectable events that are possible. So this is another likelihood of n obs given ndet. This is likelihood for the data given the parameters of your model theta, right? Or parameters describing the event. And then these are the priors. So all this expression, which looks like a humongous expression, you can break it down into parts and then understand. Yeah. No, it's not required, right? Yeah, because say if someone tells you that you are going to observe, say, 3.5 events over, or maybe like 90.5 events over, say, 1 year, right? Then you won't observe 90.5. You will sometimes, just because of Poisson fluctuations, you'll sometimes observe maybe 90, maybe 92, 94, 88, does not matter. The mean will be at that location, right? So the mean of the Poisson distribution will give you the ndet, but then there will be a variance, and that this variance, when the number of events will be large, it will go as square root of it. But it can go above or below. There's no reason for it to be just big. Any other questions? Okay. So this is the rate posterior, for example, from one of the rates and population papers from LIGO Virgo Kagra collaboration. This is from 2023. This is for fixed cosmology. They figured out, for example, what is the distribution. And in fact, there is also a rate. So how many you observe per gigaparsec cube, per year, per Emson that actually merge. Okay? And so this is as a function of M1. That's why there is Emson inverse here. And you can see what it looks like. Okay? The first thing to notice, it's not featureless, which was important for us if you want to do cosmology. If it was completely a power law, then it would have been difficult, not possible to do cosmology. But instead, because there are these peaks and wiggles, then there are features that you can latch onto. And going from one luminosity distance bin to another, you can see how this feature has moved. And that will allow you to figure out what the redshifts of these events are. Okay? This is how the Q parameter changes. So most of the events have basically very similar masses. So this is mass ratio. So M2 divided by M1, and where M2 is smaller. And so you can see that a large number of them have basically roughly the same masses. Okay. So these kind of distributions you can get. There are spin distributions and so on, which I'm not showing. You get the full posterior distribution of these parameters. Okay. Okay. So then what I told you is there are two different. So this was for fixed cosmology. Now we want to do what happens if there is a cosmological parameters. Where is the dependence actually coming from? So the dependence comes from the fact that what you observe are the detector frame masses, but you put a constraint that the source frame masses will have the same kind of mass distribution. Right? That's where it comes from. And the second thing that I told you is if there are events in a certain area, you can try to use the galaxies within that area and say that maybe they are the hosts of these gravitational wave events. And so you can use that information as well in order to get at cosmology. Okay. So what I'm going to do is I'm going to walk you through the likelihood as written in GW Cosmo. This is a joint spectral siren plus a galaxy catalog kind of method, both put together. And in the end, there is also a possibility if you remove the galaxy catalog information, just do something like an empty catalog run, saying I don't have any galaxies in my catalog, then it reduces to the spectral siren. So I'll just go through this method. Okay. So let's look at it again. What was the posterior distribution that we had written? Now there is some change of notation. This is slightly different papers, but I will again tell you what it is. So XGW is the strain data, so the gravitational wave data that you get. This tells you whether a gravitational wave event is detected or not. Okay. So you will only run your analysis over events for which you have measured the strain and that they are detected. And there will be some other information that you may have folded in. What you want is the cosmological parameters, the rate parameters, everything given this data set. Right? And so again, there's a prior, there's this Poisson distribution related to how many events you detect, and then a multiplication over the different detections of this kind of a thing, where the denominator is related to the selection effects and the numerator is related to the likelihood. Okay. So again, since we have gone through this multiple times, hopefully this will be familiar now. Okay. So now we will take a look at, I mean, this we know, this is just the likelihood, so we will not look at it right now. What we'll look at is this particular theta given lambda comma. Okay, before we go there, actually, sorry, so this, before we go there, let's look at this as well. So what is this? Probability that you see a gravitational wave event, some kind of strain data given theta, lambda, and I. What we can do is, we can say that let us divide our sky into different pixels. Okay, so let's suppose the entire sky, you make it into smaller and smaller Hill pixels. So Hill pix is a way to divide up the sky, and this you may see it in the tutorial. That there will be galaxy catalogs which will be divided up into these kind of Hill pixels. It gives an equal area kind of a division of the sky. Okay, and so what you can do is you can say that I will write this term as an integral, or sorry, as a sum over different kinds of pixels. Okay, so I'm looking in this direction, maybe in that direction, maybe in that direction, and so on. Okay. So what have I done here, right? I have, instead of having a theta lambda I, now I'm conditioning on some omega j. Okay, so I'm adding in an extra parameter omega j. Okay, and so now what will happen is it is going into the given column here and a given column here. So I need to add in a column which tells what is the prior probability that I will see an event in a particular location omega j. So this is just another way that I am just integrating out these omega j's. This will finally give me exactly this, but I'm explicitly writing it out. Okay? I'm explicitly trying to write out the dependence on the pixel value. Okay, where exactly on the sky this event is happening. Can I see the same strain if my real gravitational event was there or not? That is what we'll try to get from these kind of terms. Okay. So then, let's see, what did I do here? Okay, so if I assume that this prior probability is uniform, okay, this is a prior, right? This does not have any data set in it. So whether a gravitational wave event is equally likely to happen in this pixel compared to that pixel compared to that pixel, then it means that this I can ignore. Okay. And so you get something like this, which remains. Okay. So what did we do? We took this likelihood, we express it as a sum over different pixels, omega j. But then we also impose the fact that gravitational wave events can happen in any sorts of directions, all sorts of pixels. So this drops out and you are only remaining with this. Okay. Okay. Then what did we do? To go from here to the next, I'm going to divide this theta. So this theta is the set of gravitational wave event parameters. I will divide it into parameters that describe all these shapes and mass distributions, etc. But then I will take out, there will be also a redshift of the event, right? And so I will take out that redshift out. Okay, so this theta, I will write it is as theta prime and z. Okay, so that's what you will see here. So there will be a theta prime and z instead of theta. So that's, so instead of this theta here, you have a theta prime and z. So you'll have this xgw, omega j, theta prime z, and lambda and I. Okay, so that's what you see here. Okay. So then I should have a p theta prime comma z given these parameters. And that I'm saying is independent of each other. Okay. And so this p theta prime given omega j lambda I multiplied by pz given omega j lambda I, this I'm going to separate it out. I'm saying that these are independent quantities. And so that's the reason why I can multiply these properties. Okay. And the integral over d theta now will become an integral over d theta prime and dz. So that's what you see. Okay. Okay, so now that we have this here, so this kind of a thing you can get. So if you are given what is the location in the sky of a gravitational wave event, what this xgwi will be, what the strain will look like in your detector, this is something that can be figured out. But now what we are going to look at, so this is just the population term, okay, that we had calculated previously. If you are given the parameters which describe the shape, then this is known. Let's look at this term here. Okay, what is the probability that you get a z in a given pixel I omega j? Okay. This thing is called a line of sight redshift prior. Okay. So redshift prior towards a given pixel omega j, what is it? So let's work that out. So instead of omega j, I have made it omega I in this paper. So just take the equations from there. So P of z given a direction, some parameters. Now we have put in an S which tells you whether a gravitational wave event is seen or not, right? Because there is no gravitational wave event data which is going in here. So we have to put in a fact that maybe some of the events you will see, some of them you will not see. So that possibility is written as S. Okay. So how can you estimate what is the prior probability in a particular area of the sky to see an event? Right? So within that area of the sky, you may have certain galaxies that you have seen, say in a galaxy catalog. Maybe one of these galaxies can act as the host of your gravitational wave event. That is a possibility. Or there may be galaxies which are below your threshold, below your detectability in the electromagnetic domain, right? Just because your telescope was not sensitive when you made that survey. So you will always lose out some galaxies. So maybe the gravitational wave event has a redshift which comes or has a host which is in this population, right? So there are two possibilities. One is that the galaxy or the host of your event is in your galaxy catalog or is not in your galaxy catalog. There are two possibilities. So what do? I sum over both these possibilities. So that is what is given here. Either my event will be in the galaxy catalog, or it will not be in the galaxy catalog. Okay. What I have additionally done is I have said that there are possibilities that when you have a galaxy, it will have some absolute magnitude and it will have some apparent magnitude. So what is absolute magnitude? It's it tells you what is the total luminosity of this galaxy. What is the apparent magnitude? That is related to the flux that you see. Okay? These two are related to each other, but let's keep them separate for a moment and you will see why. Okay? So then what I'm doing is I'm just doing this integral here. So what you're seeing here is just a marginalization, right? Okay, what I'm doing is I'm putting in many terms here and I'm integrating all of them out so that I will get P of Z given these quantities. That's all I'm doing, right? So again, going back to our cheat sheet, this will be one of these formulas, but written in just simple form. Okay, so it just looks complicated, but it's simple. Okay, so this is fine. This is just going through all different possibilities. So now let's write it all down together. So this G means either the galaxy is in the catalog, and G tilde will be galaxy is not in the catalog, the host galaxy of your event. And then what I'm doing is I'm again using Bayes' theorem, okay, to go from this to this. Okay, first of all, this sum we have summed up as two different quantities. That's the first thing. The second thing is you just ignore all of this Z, MM, blah, blah, blah. This is P of G, right? Okay, so that P of G, I can write it as, let's see. So this is a G here. Right. So there is a G here, and this G, I want to put it on the other side, right? And so there is a probability of the G itself, and then the probability of the redshift M given your G. Okay, so this is the Bayes theorem at work. Let's see how we can write this down. So there is a P, Z, M, and G, given some information. And this I've written it down as P of G given my omega I, lambda, S, and I, right? Times probability of the Z, M given G. Okay? Yeah, that's what this has done. Okay, there may be some normalization terms, right, below. This is definitely proportional. Yeah. And then similarly for G prime, I can do the same. Okay. Okay. So now we have these two different terms. One is this integral and another one is this integral. So we can work it out separately. One is an in-catalog term. So galaxy is within the catalog, and then galaxy is outside of the catalog. Okay. So these two terms we can try to evaluate separately. So let's look at the in-catalog term. So the in-catalog term had redshift, the absolute magnitude, and the apparent magnitude. So the luminosity and the flux and the redshift of the event, given that your object is in the catalog and all this information, that it is in a particular pixel. So now, after this, what you do is again apply a Bayes theorem for S. This information, whether your galaxy is going to be a host of your gravitational wave event. Okay. Is there a probability? Is there a probability which depends upon some other parameters? Okay. So that's the reason why this S is kept out right now. So you bring it on the other side. Okay. So you take it to the other side again by applying Bayes theorem. So you get S given Z M M. Right? And then divided by the probability of S. So this is again a repeated application of this Bayes theorem. And then let's look at this particular quantity. Okay, so sorry, this particular thing, P of Z give comma M, given this G, omega I, lambda, and I. What I'm going to do is take this Z and M and put them on this side. Okay, so the Z and M, I have to put in this side. So again, I will apply Bayes' theorem. So what will happen is this probability, again, you can see it's P of M given Z comma M times the probability of the Z comma M given these terms. Okay. So again, this is Bayes' theorem once again. Okay, so now that we have done this, now we can write out. So what is the absolute magnitude given the redshift and the apparent magnitude? This depends upon the cosmological parameters because it's relating the luminosity to the flux, right? So given a flux and a redshift, you can calculate the luminosity. So that is this term. What is the absolute magnitude given the redshift and the apparent magnitude and the cosmological parameters? Okay. This is where the cosmology information comes in, right? To relate the apparent magnitude and the absolute magnitude. Yeah, so I think there are some probability signs, right, that are missing. Is that what you're saying? Yeah. Yeah, right. Yeah. So I think that term is missing. Yeah. So there's a probability here. Okay. So then this thing here, you can write it down to have the cosmological information. And if you look at this thing, what is it telling is, what is the probability to get a redshift and an apparent magnitude? Okay, so these are observable quantities. If you have a galaxy catalog, you know there is a galaxy at a particular redshift and has a particular flux, right? And so this term you can estimate if you are given a galaxy catalog. Okay. So in a certain direction of the sky, if you know what all galaxies are there, you should be able to figure out what this term is. Okay. But the cosmological information is coming from here. Okay. Then there is also this information about what is the probability that you select an event given the redshift and the magnitude of these events. So if you wanted to say that if galaxies have brighter magnitudes or brighter luminosities, then they are more probable to host gravitational wave events, then that will go in this term. Okay. So you can try to find out each and all of these terms in GW Cosmo, for example, okay, where they are coded up. That will be something that you should do. Because if you want to change these assumptions, you need to know where exactly to go in the code and change these things. Okay. So now that we have this quantity, you remember that there was an integral, a double integral over the absolute magnitude and the apparent magnitude. So we can carry that out next. Okay. It becomes simpler because now there is a delta function, right? So whenever you integrate over a delta function, things become simple. So that's what we are going to do. So you integrate over this capital M. You take this whole term and you will see that what will happen is if when you integrate over the capital M, this delta function will tell you that this magnitude that you get, it will be basically a function of the apparent magnitude and the lambda and the Z. So that's what you see. This magnitude, which was P of S given something, that goes as absolute magnitude is function of redshift, apparent magnitude, and lambda. Okay, so now everything is just dependent upon the apparent magnitude of this galaxy. Okay. Okay, so now that you have this, you can ask, okay, what is the probability to get a redshift and an apparent magnitude in a certain direction? That you have observed galaxies, and so you can do a discrete summation to figure out what this redshift is. Okay. So this tells you, this is basically writing down what is the probability to get a redshift and an apparent magnitude. This will look something like this. You are summing over all galaxies that you have in that particular pixel. You are saying they need to have the magnitude that I've seen. This is an assumption, by the way. This, galaxies don't come with like one apparent magnitude. They will have an error associated with it. So you can put in an error if you want. If you want to extend GW Cosmo again to account for these magnitude errors, you will put that in. Then there is also a redshift given the, so each of these galaxies that are given to you, they will be assigned a redshift. But the redshift will also have an error. And so you need to account for that as well. So that is this P of Z given the redshift which is assigned to that object. So there will be an error associated with this as well. Okay. So that will also go in. So you then plug that all in, you basically get an expression which looks something like this for this integral, so that you can go back and again plug. So remember, this is only one piece, right? So our, yeah, of the first integral, right, of the in catalog term. I think I have put in an extra slide. No, maybe after this. Sorry. Let's go back just quickly once. Sorry about this. This was the full redshift prior that we were talking about. This is only the prior, right? The redshift prior that we are talking about, we have established what is this integral. Okay. Next, we will try to do this integral, and the mathematics is very similar, so we won't take that much time to go over that integral. Okay, and then we'll put it all together to get what the redshift prior is. Okay. So the out of catalog term. So now again the same thing, redshift, absolute magnitude, which is luminosity and flux, given the fact that the galaxy is out of your catalog. You don't know in that region there are some galaxies which are missing. So what do you do about it? Okay. So again, you bring this S on the other side. So this was just Bayes' theorem. Okay. And then what do you do? Let's see. So this selection, this function, you are going to say that it does not depend upon the fact that whether your galaxy is in the catalog or out of the catalog, you are going to use the same kind of function. So if you say that my probability to host a gravitational wave event, if it depends upon the luminosity of the galaxy, it should not matter whether I see that galaxy or not. It should be exactly the same, right? So that's why it's written exactly like this. It's also assumed to be independent of which direction you look at, whether you look at in this direction or that, should not matter. So that's why this omega I term is not written out here. Okay. But then now let's look at again this term here. So this again you can do the same game of like Bayes' theorem. You take out this G bar, you put it on the other side, so you can see it's the same game that we played before. It's similar thing which is done here with the Bayes' theorem. And then now we have to understand what is the probability that you cannot see a galaxy, okay, given that it has some redshift and an apparent magnitude and an absolute magnitude and so on. Okay, what is the probability that you will not see that galaxy? So in principle, what happens is whenever you do a survey, a galaxy survey like this, you will have a certain flux limit, right? And that flux limit will dictate what kind of galaxies you see. Okay, so I'm showing you this from the Sloan Digital Sky Survey. This is sorry, what happened? This is the redshift here on the x-axis and the absolute magnitude on the y-axis. Brighter galaxies are up here because I've reversed the scale. Fainter galaxies are down here. Okay. So what do you see? You see that at low redshift, you can see all the faint galaxies as well as the bright galaxies. As you go further and further out, you only see the brighter galaxies, you don't see the fainter galaxies. Okay. And at certain point, maybe things become very unreliable, so you just cut out the survey and say that, okay, I'm not going to see anything beyond 0.2, or I'm not going to use any galaxies which are beyond some redshift. Okay. So this is the kind of surveys that you typically have to deal with. If that is the case, then now you can write down what this galaxy, the probability is to have a galaxy which is outside or which is not in your catalog. So that, what will it be? It will be either the fact that you have a magnitude or you have a luminosity which is below this threshold. That's one possibility. Or it is possible that you are above the threshold, but then you are beyond the redshift limit. Okay. So there are these two different possibilities. So you are below the redshift, so you satisfy the redshift criteria, but then you are below this threshold, then you cannot see it. Or you are above the redshift cut and you don't see it at all, okay? Or you are not in the catalog at all. So these two possibilities, yeah. Yeah. Yeah, so there is some small kind of deviations that you get because typically there is an exposure time that is given to a telescope, which means that there will be a point source sensitivity. Galaxies are not necessarily point sources, but it's pretty sharp actually. Yeah. Okay. Especially in this kind of plane, if you take SDSS data, plot it, better detectors will bring this down. Yes. But there will always be a cut. So it depends upon how far down you want to go. There will always be a flux. Okay. Okay. So you have these kind of probabilities for each of your galaxies. Okay. And then there was another term which was what is the what is the relation between redshift and the apparent magnitude and the absolute magnitude and the apparent magnitude. Again, is the purely cosmology dependent term like we saw before. So then again, you can plug all this back into this mess and then carry out the integral. Okay. So you carry out the integral and you see because there are these theta functions here, now what happens is when you integrate out these terms, you can only integrate over a certain redshift range or over a certain, say, magnitude range, right? You cannot integrate over all magnitude range. You only have to integrate over a certain range. That's because of this theta function. If you remember the theta function, it basically is 0 and then it becomes 1, right? And so after a certain point, you will have to integrate. In principle, it goes out to infinity, but there is a choice that people make, like how far you are going to integrate. And so these choices are basically dictated here. Okay. So this is the out of catalog term. So this is another integral that went into our redshift prior. Okay, so this is just the prior. But this is important, right? So it's the redshift prior where all this galaxy catalog information is going, which tells you in this direction, what are the kind of redshifts that we expect for our gravitational wave events. Okay, so this was that original expression. And so we have calculated what this is, we have calculated what this is, so then we can plug it back in. Okay, so again, it becomes another messy kind of calculation, but you walk through it one by one. I'm not going to bore you with this anymore. Okay, and then you get basically what this redshift prior is going to be. Okay. The in-catalog prior, you will write down as a sum over possible redshifts that are given in the catalog, okay, for your galaxies. And then the out of catalog term, you have to worry about what are the missing galaxies. Okay. So those, once you know what are the missing galaxies, then you can figure out what this out of catalog term is. Okay, so then this is the part that was also missing. What is the probability to get a gravitational wave event given these parameters that you have? So the redshift, the absolute magnitude, lambda and I. So this thing, typically it's divided up into two possibilities. One is that this selection can depend upon the redshift and it can also depend additionally on the magnitude of galaxies themselves, like what is the absolute luminosity of your galaxies. So what this term allows you to do is if there is a dependence, let's say, on the star formation rate, then you can put it in. So as you go to higher and higher redshifts, because there is a lot of star formation, maybe your merger rates are going to be higher. So that you can put that in this term. Okay. While this term will tell you, given a galaxy of a certain luminosity, what is the probability that you will see a gravitational wave? Okay. So low luminosity galaxies, if you are going to give less weight, then it will go here. So this kind of separability is also done. Typical assumptions are that this P of S given M, I is assumed to be proportional to the luminosity. But then you can ask luminosity in what band, right? Because if you look at different bands, then they are sensitive to different things. The bluer bands are sensitive to more recent star formation rate. The redder bands are more sensitive to the total stellar mass of your galaxy. And so it's a question, what exactly will you use, which bands will you use, etc., etc. So there are uncertainties like this that also go into this analysis. You can use uniform weighting, saying that all galaxies are equally likely. That is also a possibility. So these two possibilities are coded up in GW Cosmos so that you can check if you make one assumption, what do you get? If you make the other assumption, what do you get? So all these kind of systematic tests are run when the final cosmology analysis is published. Okay, so this line of sight prior, this depends upon the location of the pixel. This can be pre-computed. Okay. The reason why it can be pre-computed is once a galaxy catalog is given, then you know what are all the galaxies in a particular pixel. You can directly compute it. You don't have to do it each and every time you are given a certain set of cosmological or gravitational wave related parameters. So you pre-compute it for computational reasons. So this kind of pre-computation was also already done in the GW Cosmo files that are given to you. And so you will see this line of sight prior related file. It will be basically this. So in each and every pixel, it will write down what is the probability to have a particular redshift. So in the tutorials, try to see if you can access this file, if you can check the pixel number for which it is applicable. That pixel number corresponds to a certain array deck location in the sky. You take a look, what does this prior probability looks like? Okay. Okay, good. And then the other part was the calculation of the selection effects that I told you about. So the calculation of the selection effects, it's basically what is this gravitational wave event detection probability given the different parameters that you have for your events, at what redshift they are, and so on and so forth. What is the prior probability of this, and integrating over all possible parameters, so dm1, dm2, dz. And so this has a dependence upon your shape parameters. So what you do is you basically run injections based on some prior probability. Okay, so this is the injection probability. You run the injections based on some prior probability, and then you have many samples. So NSIM simulated samples. Okay, and from there, now you take out this prior. Okay, so there is an actual probability that is there, and then whatever you had assumed to be your prior probability. So you can use that in order to figure out what the selection effects will be given the parameter set that you have. Okay. So the simulations for these are called injections to understand the detections and the selection effects. That can also be pre-computed. You do it once, you store these values, and then you know what this prior probability is, so you can take it out. In reality, what you want is this integral. You can do it by using the already existing injections. So you will again see a catalog which has these injections and which calculates the value of this detection probability. And then that can be used in order to calculate these detection effects given the parameter set. Okay. So all of these things that we are learning here, there is some counterpart or the other within the tutorials. We will only show you how to run these tutorials, but to go back and to figure out where each of these terms are and how they join together, or to plot some of these terms by yourself, that will be a job for you. Okay, and it may not be done over today and tomorrow, but you may have to go back and try to do these things by yourself. Okay. Everyone with me until here? I don't know. It's complicated, all these mathematics, but you just work it out once and you will understand. At least I've tried to give you the reason behind each of these terms. Okay. Okay, so when you run any sort of Bayesian analysis, you need to state some of your priors. So you can state the priors, for example, for this. There are different parameters which describe the shape of your distribution. And so these are some of these parameters. What is the minimum mass of some power law component of the black hole mass distribution, or the maximum mass that you can have, what is the spectral index for the power law. Then there is a peak. So you saw that there was a power law and a peak. So where exactly is this peak? Okay, so that's the mean of this Gaussian component. What is the width of this peak? That can be another component. What is the fraction of things which are within the peak and outside the peak? So within the power law component and outside in this peak, you can move them up and down, right? So that parameter is this lambda g. Okay? Then there is a smoothing that is done, and so on and so forth. Okay. So there are parameters which describe the shapes. Yeah. Yeah, so you look at the rates and population studies, they will have certain models which will fit the data best. You don't use exactly those parameters, but you use the models as priors. So you are saying that, well, maybe it's power law plus peak that fits best. Just the simple power law with truncation does not work, for example. Or you can have multiple peaks, so multiple different Gaussian peaks. Okay? And then it becomes a model selection business, right? So given the data, can you prefer one model over the other? So that is also something that can be done. Yeah, so typically people do it using evidence in the case of LVK. So you will calculate the evidence, and then the evidence will tell you using ratios of these evidences, which model is preferred. AIC and BIC are like point criteria, right? So instead of this, you use a probability, some kind of odds ratios. So these evidences are, that's the reason why people use nested sampling as well, because that directly gives you the evidence. And using that evidence, you can calculate whether your model 1 is more preferred or model 2. Yeah. Yes, yes, yes. Right, yeah. That needs to be done, right? So some kind of cut you will put in, and so because the detectability then, sorry, no, in this case, the dz integral will go out to infinity because galaxies are only present until then, but your events can be present out to a large value, right? And so this dz integral here for the selection effect will go out to large values. Yeah, so that will come here, right? Because it is in the in catalog terms and in the out of catalog, that's where this information comes in. Exactly, because there will be still galaxies which are beyond, but then that is completely out of catalog. So you don't know what the exact redshift distribution is. You will have to guess, right? So how to come to that guesses, I will also come to. Okay. So then there is also this model, as I told you, how to select, like what is the probability that you will see a gravitational wave event given the redshift. That is given by this kind of, again, some parameters which describe this particular behavior of how the rate changes. This is motivated by how the star formation rate in the universe changes. But the parameters are left free. Okay, so they are not put. I mean, these parameters are basically parameters that you need to constrain from the data itself. So you do this, you run something called nested sampling to figure out what the posterior is, right? So this is what is that, how to calculate the posterior using these nested sampling methods is what GW Cosmo and Ikaru GW will do. Okay. So once you do that, you will get plots like this. And so they don't tell you exactly the posterior, but they will give you samples from the posterior. And so these samples are what are plotted in these kind of corner plots. So what you are plotting is H naught versus say sigma g, H naught versus mg min, H naught versus this m max, H naught versus mu g, and so on. And then all parameters basically against each other. Okay. You take those samples and then you draw these posterior distributions. And you can see that there are lots of degeneracies, right? Especially when you are determining H naught, you can see that there is a degeneracy to the maximum black hole mass. Okay? Because if there is a sharp cutoff that you are putting in your model, then how that cutoff changes will change how the redshift information that you glean from your data will be, right? How it will look like. And so that's the reason why you get this kind of degeneracy. There's also degeneracy with mu g, right? So where exactly you put in the parameter which tells you where the mean of that Gaussian is in that mass distribution. So if you change it a little bit here and there, you can change the H0 values. So there is a degeneracy between these population parameters and the value of the Hubble constant. So in earlier papers, what we used to do in the LBK collaboration was that the population parameters were fixed to the parameters that were found in previous analysis. So if you do that, then of course you get much better constraints on H0. So you would see that earlier constraints on H0 from LVK collaboration were quite tight. But then we realized that, yeah, I mean, there is this degeneracy. We should not fix them. We should allow them to vary. And once we do that, then the range increases. So the allowable range of H0 increases, yeah.
Choice of sample of the procedure is done independently or what?
No. This is nothing to do with the way the sampling is done, because this actually tells you what the posterior looks like. Okay.
It's perfectly like circle, not like a...
I mean, for some things, I mean, here you look, there's like a huge degeneracy. You cannot constrain sigma g necessarily, right? I mean, there are things which you start to see some kind of a deviation here. So exactly what the mu g is and the spread is, that is degenerate. So yeah, I mean, maybe that is expected as well. So, I mean, there are degeneracies. You cannot perfectly fix everything. But what you can ask is, given all these parameters, how does the mass distribution look like? Right? And that I think I had shown it for fixed cosmology. It will just broaden a little bit more when you allow for cosmologies to be made free. Yeah? So that, for example, let me just quickly go back to some slides. It's harder to do it from here. So this thing, sorry. So this thing that was done using fixed cosmology, now you will get something similar, but it will be a little bit broader now because of the degeneracy with H0. So now there will be a broader range which will be allowed. Yes. The dark and light were uncertainty contours, right? Yeah. So there will be like 68 or 95% contours that will be shown. Yeah. Some sigma, basically. Yeah. I don't remember the choice that was done. Typically, I think it's like 68 and 95, but I will have to check. Okay. So I think I talked about all this. Okay, so then these galaxy surveys, let's try to, I think I talked about anyway some of this, so I'll go through quickly. Luminosity on this axis, redshift on this axis. You can see now, because I've blown up the plot, how sharp it is. But there are a few points here and there which will also go. So that depends upon the size of these galaxies sometimes. Okay, and so the part here is something which is seen. Okay, you can see these parts, you can pinpoint a galaxy, you can pinpoint what its magnitude is, its redshift is. This is a spectroscopic survey, so the redshifts are much better measured. But you remember, we had some integrals which went over this population. So how do you carry out that integrals over that population if you don't know what is there? Right? So that will be a question that we will have to deal with. How to deal with galaxies which are actually missing. Okay. And what is happening is, this statistical host identification method that is there, what it says is that either one of these galaxies is your host or one of these galaxies is your host. It does not account for the fact that galaxies here and here, they can be actually correlated. So even if the host is not present in the catalog, if there is a brighter galaxy which is also in the same region but at the same redshift, then that can also give you some more information about what the redshift of that event is. That is not taken into account at all. So then your statistical host identification method, it really depends upon what is also going on down here in the incomplete sector. Okay. And so this incompleteness is also something that we need to worry about. Okay. So how do we deal with some of these incompleteness? First of all, given this kind of survey, when people make galaxy catalogs, they don't have one galaxy catalogs. They have many, many such galaxy catalogs which are spread out all over the sky, because some telescopes can only observe this part of the sky. Some telescopes will only observe some other part of the sky. Like in the northern hemisphere, you cannot see all the sky from the southern hemisphere, right? So all of these telescopes will have their own limitations. Telescopes don't usually go down to very low latitude, low altitudes, because there is a lot of extinction that will happen from our own atmosphere, right? And so there will always be limitations. So the galaxy catalogs that are used in these analysis will be a compilation of different catalogs, not just one catalog. And so here you can see this is based on, I think, one of the Glade Plus catalogs. You can see what kind of a catalog this is. This is only above some plus 15 or maybe plus 10 degrees in terms of declination, so away from the equator. This thing here is the Milky Way plane. Okay, so through the Milky Way plane, you cannot carry out a survey. So there are galaxies which are completely missing there. Can you tell me why there are more galaxies missing here and less galaxies missing here? Why that might be? Exactly. So this is like more towards the galactic center, while this is, even if the disk is there, if I'm looking on the other side of the center, central part, then I can still see some more galaxies. Well, you can still see, I mean, there's a lot of gas and dust, so you do see extinction. Okay. So this you have to deal with. It means that you cannot use just a simple one single magnitude threshold for your galaxies. Your magnitude threshold will be dependent upon, or the flux threshold will be dependent upon what position you look at in the sky. Okay. So this was the extreme example. You can't see anything. That's one. The other possibility, what I'm showing you here, and unfortunately this has gone missing, is this magnitude threshold on the entire sky. Okay, so you can see all sorts of crazy patches, right? You can see these stripes here. Okay, so these stripes are coming from the Sloan Digital Sky Survey. So this Sloan survey, which had done the spectroscopic survey, especially the initial parts, there was a northern galactic cap, so the northern side, which was observed. And when I say north, it is north compared to the disk of the Milky Way. So this is the north side, and then this is the southern side. Okay, so the southern side was done in stripes, and that's the reason why you see these stripes. In the northern part, you can again see the inhomogeneity of the survey as well. I think this was some earlier release that they had used, and that's why it's quite inhomogeneous. And so all these things you have to worry about. There was some other survey which was quite uniform. But then you try to use the deeper data wherever it is possible, because if you have more galaxies, you get a better prior. So you use the deeper data, right? And so it's basically this kind of a mess. It's also, I mean, even within these surveys, what you will see is, if you zoom in more and more, this is just showing you a bird's eye view of the surveys. If you zoom in more and more, you will start to see that if galaxies are close to, say, certain stars within our Milky Way, you cannot really keep your telescope pointed at that location for a long time, because these stars are nearby, then they appear also brighter. And if they appear brighter, you have a big telescope which is integrating all this light, then it will create a big hole on your CCD, right? So the imaging surveys also have holes. And so you cannot target galaxies to obtain the spectra. So then all those survey inhomogeneity effects will also come in here. So those are also things that you will then have to worry about. Right now, the way the analysis is done, I don't think people are fully accounting for all of these effects right now, okay? But there are all sorts of these problematic things that are present in the galaxy catalogs. Okay, so this shows, for example, these magnitude thresholds. So these are done on different kinds of maps with different resolutions. So this, I think, is a more low resolution map. I think this one is what is provided to you, the 32 n-side map. Okay, so this you may see it in your tutorial files. So what this n-side of 32 means is that the number of pixels that are there on the sky is 12 times n square. So if you do 12 times this 32 square, you should get this. The whole sky is 42,000 square degrees or so. So you divide by this number of pixels, you get roughly 3.36 square degrees. So it's these big pixels on the sky over which you calculate what this magnitude thresholds are. Okay. So this is now a more recent version, and that's why you see that they have put in more and more galaxy catalogs even in the south, and so that's why they have a better coverage. But still the Milky Way plane is gone. You can see where the center of the galaxy may be. Okay, and so this map you can see at a map of 32. This is what happens when you do a more higher resolution map. Now you can start to see even holes, right? Because when you do a coarser map, you don't see these holes anymore. You do a finer map, you start to see all the holes which are also present. But each of these pixels information now you can put in. So this is more granular information. This is less granular. Try to see what happens, right? If you use this map compared to this map, do you get a different, like large change in your H naught posterior? Those are things that you can check out. But someone has to figure out what this magnitude threshold is as well, right? So how do you do that? Okay, so this is the last thing that I will cover before we go into, before we go to the tutorials. So how do you compute the magnitude threshold of galaxies? If you are given a galaxy catalog, what will you do? So currently what is done in the collaboration is that you take all galaxies within a pixel, you make a histogram of magnitudes of these pixels. Okay. So let's suppose that this histogram looks something like this. Okay, so there will be very few, so brighter is here. Okay, and fainter is on this side. So there will be very few bright galaxies anyway. Okay. As you go to fainter and fainter objects, this should also keep on getting larger in principle, because there are many, many faint galaxies intrinsically in the universe. But then what happens is you start to not see these faint galaxies after a certain point. And so then this starts to go down. So right now what is done in the collaboration is to take the median of these galaxies. So this is some kind of a probability distribution of the magnitudes. So you take a median where you will throw away half of these, which are fainter than this median, and say that my magnitude threshold is driven by this median. So anything which is brighter than that, I will keep it in my catalog. I will throw away half of my galaxies. That's what is done right now. So again, try to look for code which is calculating this median and trying to figure out where these magnitude thresholds are or what they look like. Okay? But there is a first principles approach in order to do this as well. And that's what I wanted to tell you. So this is work together with one of my PhD students. So what we did is we started from first principle. We asked, what is the apparent magnitude of galaxies really? Right? It is related to the logarithm of the flux that you get out, that you observe at your telescope, plus some 0 point. Right? So some flux you say gives me magnitude 0, and you compare it to that flux to tell you what is the magnitude. Right? That is what you do to get any magnitude whatsoever. So the error on this magnitude will be related to this flux like this. So this m naught will cancel out because you use the same 0 point. So when you take a dm, this will go away. Because you are taking a dm, this thing is a logarithm with respect to base 10. So it is ln of f divided by ln 10. That's this ln 10 here. And then ln of f, the derivative becomes df by f. Right? Okay? So the magnitude is related to the flux and the error on the flux that you have. So typically when you detect galaxies from a galaxy survey, what will you do? You will ask for the galaxies or whatever detections that you have done to be above a certain SNR threshold, right? So some signal to noise ratio they need to have, okay? So what will happen is you will take an image. It will not come up with, okay, I'm a galaxy here, I'm a galaxy here. You will have to figure out where are the galaxies, right? So there will be certain photons, you will see some excess of photons. And so that one is the one that you will tag as a galaxy. But when you see an excess, you will also have to worry about whether this is just a noise peak, right? Just because there are noise fluctuations, you may think that that is a galaxy, but it may really be a noise. So then you have to put in a noise threshold, right? So some kind of SNR threshold. And that SNR threshold will be, say, let's say on the flux, right? So F divided by DF should be at least 10. Maybe you will say something like this, right? That this SNR threshold may be F divided by DF should be greater than or equal to 10. If that is the threshold that you set, then it means that there will be it will correspond to a particular error on the magnitude. Okay. And that error on the magnitude is also given in the catalogs typically. So what you can do is, within a particular pixel of the sky, you can plot what is this error on magnitude as a function of the magnitude of the galaxy. Okay. So as you go to brighter galaxies, so these brighters are here in this case, because I have not flipped the axis again. Sorry about that. So brighter galaxies are here, fainter on this side. You see that the error bars, so let's just look at one of these lines here. The error bars are smaller when you look at brighter galaxies. They are larger when you look at fainter galaxies. The different dots that you are seeing are different galaxies in that pixel and having magnitudes in different bands. Okay, so typically these galaxy catalogs, they come with imaging data, and the images are taken within particular wavelength bands. The names of those bands are given here. Okay, so in each of these bands, you can ask, okay, what are the galaxies? What do these errors as a function of magnitude look like for this case, for that case, and so on. Okay. So now if you have a SNR threshold, you can say that, okay, what does it correspond to for my sigma of m? And then that can be used to identify what is the magnitude threshold really. Okay. And you can do this now uniformly all over the sky. Okay. Rather than completely throwing out like 50% of your galaxies and making these kind of conservative choices, then now you can do it a little bit better. So that's what it's trying to do. If you uses a SNR threshold of 10, then just a moment, then you remove out like 27% of these galaxies. If you go to SNR of 15, then you remove out 60% of the galaxies. And this is what you get with the median values, right? You can get maybe a little bit more of the galaxies, but then you have to be sure that your galaxy catalogs are really doing this kind of SNR thresholds or not. Okay. So when you are compiling the galaxy catalogs, whether they are really doing this or not, that's something that you need to check. Yes, sorry. Oh, here? Yeah.
Particular pixel.
Yes.
So a particular pixel will have all the averaged out of whatever that is seen. There are multiple things. There will multiple galaxies or whatever is there.
Yeah.
That will be averaged out to a single number.
Yeah, so typically what happens is when you use these surveys, these are large surveys that are carried out. So, there are many, I mean, the catalog is on much larger scales than the size of the pixel. So, but you are absolutely right that there will be cases at the edges where there will be half the time one survey and half the time another survey. That you cannot deal with. So, yeah, I mean, once you have a setter resolution, you cannot do anything. But you can actually flag out those pixels. Do you know what will happen in those pixels? Sigma m as a function of m, you will get, instead of getting like one nice line that you see here, for this, just this brown, okay? So ignore the different colors, because the different colors are galaxies in different bands. That is okay. That's not a problem, okay? But within the same color, instead of seeing one locus, now you will see two loci. Because one survey may be fainter, another survey will have gone maybe only brighter, right? The limit may be different. And you can flag those pixels. Then you can subdivide them. if you want. Okay. So all of these things can be done if you go to this method rather than relying on the median. Once you do the median, there is no way for you to know that a given pixel has two different magnitude thresholds or one. This completely lost. But in this case, you should be able to see. And because galaxies are not point sources, that's why there will be always a scatter. But that's okay. I mean, that is irreducible. That you cannot get rid of. But these aspects you can do. Like this problem that we have, that can be done. Of course, it takes more effort to do this. This median is much easier to do. So that's why people have been doing this so far. But maybe after some point, people may want to move to this better methods. So it may increase the number of galaxies that you have. So you can see here. But if you use an even more stringent SNR cut, then of course you get rid of some of the galaxies. But at least you have a principled way of doing the cut, which is the same in all different pixels. Okay. Okay, so maybe there's things about K corrections, etc. We'll get to tomorrow. Okay, let's stop here. And then in the tutorials, we will continue to at least learn to learn how to run GW Cosmo. And then if time permits for you, you should try to go to each of these codes and try to figure out some of these terms where they are used. Okay. So that will give you a little bit more insight into the code. Okay, thank you. Yeah.
So let's all proceed outside for the group photo session.